So I'd like to welcome everybody to the Stitch Fix Algo Hour. Today's presenter is Dr. Art Owen, who is a professor and chair from the stats department at Stanford. And his teaching focuses on applied statistics, including experimental design of Monte Carlo methods. He is best known for inventing empirical likelihood and for work on randomized quasi-Monte Carlo methods. I think also Art is the first person to give us feedback on the Algo Hour as the initial conversation starter that led to him giving a talk. So this is very exciting. This is why, they always say feedback is a gift. And in this case, it led to him giving a talk, which was even better. So thanks, Dr. Owen, and looking forward to hearing what you had to say on tiebreaker designs.
Well, thanks, Brian. It's fun to talk at Stitch Fix. I've just seen all the cool things that people do when they come to our industrial affiliates meeting. And we're starting, it's 2:07. When would you like me to wrap up and take questions?
I think leaving 7 or 8 minutes for questions is usually great. And then sometimes people can stay longer and ask more.
Okay.
But we'll play it by ear.
All right, great, thanks. Okay, so I'm going to talk about tiebreakers. This is joint work with two people, Hal Varian at Google and a student here at Stanford, Dan Kluger. And Stanford likes me to tell you that some of this was done for Google, and it wasn't something that Stanford paid me to do, it was something Google paid me to do. And then, however, I kept on working on it after I stopped doing this with Google. So I segued and started doing it at Stanford too. Okay, there are two papers. This one with Dan Kluger just hit archive like yesterday or today. And this one with Hal Varian, it's in the Electronic Journal of Statistics. So if you go to Google Scholar and you look for me and tiebreaker designs, those are the things that you should find. One thing I like about the algorithm hour is they ask the speaker for a take-home message. Okay, so here's the take-home message, randomized. So when it's feasible and of course ethical, shoot a little bit of randomness into your decisions. I mean, not too much, but some randomness. And the context, if it's a decision that you're going to be making repeatedly, and you're going to do this thousands or millions of times, if you shoot a little bit of randomness in there, then you can watch what's going on. If it's a one-time decision, then no, don't, that's different. And the thing that got me thinking about this was customer loyalty plans. So suppose you have an airline and pandemic ends and we get lots more people flying, and the airline can give a first class seat upgrade. Of course, they can't do it to everybody. They can give it to little n out of big N. Okay, so who should they give the upgrade to? And I always thought that they gave it to their n most loyal customers measured by miles or dollars or something. And I saw a story in the newspaper that, maybe what they'll do is they'll give it to the people they think they're going to influence. So you could imagine, maybe Delta wants to grab somebody who's been flying on United. And if they think somebody's flying on United, maybe they give that person a first class upgrade on Delta to try to snipe a customer away from a competitor. Or maybe you just, if you think somebody hasn't been, flying enough, maybe a first class thing will do it. Or maybe it'll egg them into flying first class when they were doing business. Okay, so there's two different things that you might have in mind when you're handing out the upgrade. And of course, hotels and car rental companies have that. An e-commerce platform, maybe they want to do something. Maybe they want to do something for their advertiser, give them a free tool that they can use to their advantage. But it would make sense and add value for the biggest advertisers, but not all of them. Or maybe you have, maybe you're hosting videos and you could give some of the people, studio time, but you can't maybe give it to everybody. Well, who would you do it for? You could reward the best customers, or maybe the ones that you think it's going to change the most. So you have two goals. You're going to make some kind of an offer. Maybe you just give away a t-shirt, but you want to get the most value from that offer. And you also want to measure the causal effect of the offer that you're making. So it's a trade-off. You have two goals: maximize the value, but also measure it. Well, I'm going to be looking today at two acronyms for those two goals. One is the randomized controlled trial. Usually it's an A/B test. And I'm going to assume everybody's kind of seen that. And the other is a regression discontinuity design. And a lot of people in industry have seen those, but not everybody has seen them or used them. And then we're going to smush those two together. We'll hybridize them. Well, here's how regression discontinuity works. And here's a famous example. It might have been the first example. You have all of these students taking a standardized test. Maybe they're high school seniors. And suppose they score high. Maybe they get more than 1,700 points. Then they get a National Merit Scholar or some kind of award or an honor, maybe money, something. And then you look at what happens later. Did they graduate in a timely manner? Did they go to grad school? Future earnings? There's a lot of things that you might measure. And you want to know, is it perhaps because of that award? But the highest scoring students were probably already more likely to go on and do those things. So you kind of want to separate out the difference between those that were already going to do more and those that did more because of the award. And here in an extreme case is the reasoning that you could use. Imagine a student that got 1,701 points and they just barely qualified. And there's some other student that only got 1,699. You would think these students are probably very close to equal talent and equal likelihood to succeed in the future. So if you see a big difference between the 1701s and the 1699s, it's probably because of Z. So it's a pretty credible, I'd say the second most believable causal inference idea is that any difference between these two groups, you can think of it as causal. Well, here's another example, and I'm going to show you data from this example later. Are students going to learn better in a small classroom? And we're thinking elementary students. And observational study could really mess it up. Like maybe that small class is actually the enrichment class, and it's just a handful of students that have done the best and are predicted to do the best, and they might really learn more than the students in a large class, but it wouldn't necessarily be because of the classroom size. And then a different principal might put all of the students with difficulties into one small class together. And they could be learning difficulties. They could be discipline difficulties with, say, an ex-military teacher. So the class size itself, it's going to be confounded with other things. You can't quite get it from an observational study. But then here's an accident, say a statistical accident that gives you a clue to causality. It's called Maimonides' rule. In Israel, there's a rule that says a classroom shouldn't have more than 40 students. And if there's 41 fifth graders, they'll make two classes, maybe 20 and 21. So the class will get split in two if it's more than 40, but it won't necessarily get split if it's below 40. So then what we can do is we can look at students who were in a class that just barely got split into small classes, or another class that just barely didn't get split, and to compare the differences. So here's how regression discontinuity might work. We have this running variable, also called an assignment variable. And let's look right around here as a threshold. Anybody on this side got the treatment. Maybe it was a t-shirt that we give them or some other swag. And on this side, they didn't. And if we look at the average for the people that just barely got it versus the ones that just barely didn't, this difference seems like it should be reasonably interpreted as causal, the barely positive versus the barely negative. And again, what about these ones? Maybe we should extend the line. Oh, now it's starting to trend up. And what about these ones? Well, where do we draw the line? Okay, that gets slippery. And you would want to take more because you'd get more statistical power, you'd get more data. Of course, if you extended it all the way, then you lose the story about it being just barely over versus just barely under. And here's what people might do. They might fit a linear regression. So we'll have a linear regression on the right, linear regression on the left, and now we see this difference here, which we interpret causally. Still a little problematic. Like, what about these data over here? If they had come out a little higher, this line would have tipped down a little shallower, and we would have interpreted a bigger causal effect over here. So we kind of want to use these ones, but it's maybe a little bit risky to use it with a linear model. And so suddenly, what seemed like a compelling and obvious and straightforward thing to do actually becomes a little bit slippery. You go down a little bit of a rabbit hole, and we'll look into that later on in this talk. Okay, now I will introduce to you the cast of characters in a simple model. So index I, that's the customer. Xi is the running variable or the assignment variable. And then Zi is a treatment. It's a yes, we give them the t-shirt. It's a no, they don't get the t-shirt. And then we have a key performance indicator, some outcome. And you have a business problem deciding what's going to be the outcome. Like maybe it's revenue 1 year later. And again, maybe it's profit, or maybe it's the increase in revenue, or you could imagine a bunch of different choices. But we have one real valued outcome. And we have this treatment to give, and that outcome, let's see, of course, the outcome is a business decision. And then the running variable, it might just be simple, like how many miles did they fly? What's the past revenue? Or it could be something more complicated, like a machine learning prediction of how good that customer is. And now I'm going to simplify this. Recall that all models are wrong. This one's wrong. So first simplification, just to make it easy, half of the ZIs will be 1 and half will be -1. Now, you would never give half of the customers an upgrade. We can undo this later. But to simplify the analysis, let's just say it's 50-50 whether somebody gets the incentive. And then what about this rank variable X, the running variable? I'm just going to sort it from smallest to largest, and I'll redefine it as a linear rank transformation. So the ith one, I'll just recode it as a linear function of the index I. So that goes from -1 to 1, and they're equally spaced. Okay, so that just makes things easier. It makes things easier enough that we can get mathematical and computational analysis to understand what happens. And then the model is going to be two-line regression. So how much y do we get from customer I? Well, there's an intercept. There's a slope for the running variable. There's a dummy variable or an intercept change according to whether they were treated or not treated. And also the slope changes whether they're treated or not treated. And this is a pretty simplified model, but I feel like it's a reasonable model. And to do some theory, you have to have at least some model to do. And then later I'll talk about what happens in more realistic settings. So I'll talk about some more realistic things. But this model is clean enough that we can see what happens. We can just see everything. Okay, now it's time to tell you what's a tiebreaker design, which I didn't even say before. So we're going to pick two cutoffs, a cutoff A and a cutoff B. And then we have this variable Z. If the X is really big, then they get the incentive. And if it's small, they don't. And in between, it's random. So here we have the running variable from -1 rescaled up to +1. Everybody on this side gets the incentive. Everybody on this side doesn't. And in between, it's a 50-50 coin toss. Okay, now, by setting it up this way, if we squeeze A and B together, we have a regression discontinuity at the common value. So you just imagine this A comes into the 50% to the middle, and the B comes in and meets at the middle, and then we have regression discontinuity. The other extreme is we could take this A and we could shoot it out to the left, below all of the subjects, and we can take B and scoot it out to the right, above everybody, and now everybody's in between, so everybody's random, and it's a randomized controlled trial. It's also called a cutoff design. The tiebreaker is also called cutoff. Okay, so we can dial it in. We can dial in a lot of experiment or a little experiment. It's up to us. And here's some examples. It's the most detailed example I can think of is one in the state of Nebraska. It was some scholarship funds by Warren Buffett, and Josh Angrist looked at it. And what they would do is high-ranking high school students would get a scholarship to go to an undergraduate in university. Low-ranking high school students didn't get the scholarship. And then in the middle, it was random. And that, I think that's really kind of bold. Could you imagine you're in that high school and your friend got a lower score than you, and your friend with a lower score got the scholarship and you didn't? Imagine doing that. That's, I guess that's something a statistician might have trouble doing. But anyway, they did it. And here's one where they're going to rehab was done with a randomized, with a tiebreaker design. There's a famous old story about Lanarkshire milk experiment. They were offering milk, free milk, to school children in the, I think it was the late 20s. And the people were actually quite, this was in the UK, and the living standards were extremely low back then compared to what we're used to now. And so a lot of students just didn't have enough food and calories to get through the day. And so, so they did an experiment where some students would get no milk, some would get milk, some would get a different kind of milk. And they wanted to see, like, is that going to actually improve their health some months later? What happened was some of the school administrators decided they would give the milk to the students they thought most needed it. And that, of course, completely messed up the experiment. It was in terms of causal inference. And then student wrote about it some years later. There were other issues in that paper, in that work too. Maybe a tiebreaker would have worked. Okay, so here's a picture of a tiebreaker.
Sorry.
Yes.
In the table there, where you're presenting these previous experiments,
Yes.
the z-value corresponds to the discontinuity.
Yes.
Are there any A's and B's yet for this sort of tiebreaker design, or none of these are tiebreakers yet?
No, these are all tiebreakers. So what they would do here, if the reading ability was low, then the student went to remedial English.
Okay.
If the reading ability was high, then they didn't. And in between, it was random. Actually, it was random whether they were recommended to go. So there's an intent to treat angle. And this one on rehab, the people in the worst shape went to rehab, the best shape didn't, and in the middle it was random.
Okay.
Yeah.
Okay.
Thanks. Okay, so if we do a randomized controlled trial, and I've got the red points that got the incentive and the black points that didn't, it's hypothetical data, and A and B are way to the left and right, it's pretty clear that the red points are riding above the black points in this picture. If we did a regression discontinuity, the red points are riding along on a higher line, but it's harder to see. If we sneak in a little bit of delta so that 1/3 of them are experimental, it starts to become clear that the red points are higher than the black points. Not as clear as here, more clear than there. And a 2/3 experiment makes it more clear than a 1/3 experiment. So visually, the more you experiment, the more you can see the difference. Okay, so now let's do a regression analysis. And if you recall from the class on linear models, we'll have this linear model relating y to what's got an intercept, it's got our running variable, it's got our treatment variable, and an interaction that can change the slope. And so we make our big X matrix. It's got a whole column of ones. It's got a column of X's, a column of Z's, and a column with the product. And now what is the variance of beta hat? Well, it's X transpose X inverse sigma squared. Okay, standard formula. This is the variance conditional on the Z's. Okay, and then what about those Z's? Well, if X is small, there's no chance that it was a 1. If X is large, for sure it was a 1. And in the middle, it's 50-50.
So wait, Zach here. So question, like this kind of has a flavor of a bandit, right? It's not a bandit, but it like.
Thank you. That's a great question.
I'm wondering kind of like, what is this assumption of equal probability within a range get you?
Well, so we're thinking of things where you can't do a bandit because it might be a year before you measure Y. And in the Nebraska setting, they would give a student a scholarship and then they would find out whether they graduated within 6 years. So if you get your next Y value after a 6-year wait, that's not a good situation for a bandit.
So I guess better way of framing it would be less about the adaptive component of the bandit and more about how the probability of treatment will change based on where you are.
I have a slide on that later. Like here, we're just saying there's only 3 levels. There's nothing, 50-50, and for sure.
Yeah.
And when we started this, we thought, we should have a sliding scale.
Yeah.
Yeah, okay, I have a slide on that later.
Okay.
Yeah, thanks. Okay, so what's X transpose X going to look like? Well, 1 over n X transpose X, that's just averaging the squares and cross products. So 1 times 1 is always 1. The average of 1 is always 1. Okay, so this one's a freebie. The X's are, by construction, they average to 0. And the Z's, by construction, they average to 0. What about X squared? Well, we'll calculus integrate X squared from -1 to 1, where the average is going to be 1/3. What about Z squared? Well, Z is always 1 or -1, so Z squared is always 1. So the average of Z squared is always 1. And if I take XZ, I get X squared Z squared. Well, Z squared is always 1, so that's just X squared, which we already saw was 1/3. So they're all easy except this. Up here, I want to know what's the average of a 1 times XZ. Over here, what I want is the average of X times Z. That's actually the same as 1 times XZ. And then down here, this is the average of Z times X. Okay, it's the same as this. And then this one. So there's one missing number that goes down this reverse diagonal. And we can use a little bit of calculus. So what would that look like, that off diagonal, those elements? Well, they're just the average of X times Z. So X is uniform -1 to 1. So we'll average over X. Then we'll average over Z given X. And at the low end, Z is always -1. At the high end, it's always +1. In between, it averages to 0. So the calculus says it's 1 minus delta squared over 2. So we can go up to this matrix and we can pop in 1 minus delta squared over 2. And now we have the whole thing. And this wiggly line, that's like 1 over root n sampling error. It could actually be more like 1 over n error if you did a stratified sample, which is what we end up doing. Okay, let's reorder the columns. Instead of going 1x, zx, we'll pair up the 1 and the zx, and we get a 2 by 2. And then we get zeros. And then down here we get zeros. And then here we get the exact same thing for z and x as we have up here. Okay, so now I can invert that matrix with my bare hands. I don't have to think about it or do it numerically. And then n times the variance of beta hat, it's, well, that phi squared comes in. Wait, it's numbers that I know, 1s and 1/3. Sigma squared that I don't know, I'll get rid of it later. And I've got some minus phis, and I've got a 1/3 1 minus phi squared. Okay, and then phi is just this function of delta. Okay, so I think I can handle that. And then what delta do I want to use? Well, I want a small variance. So the variance of C transpose beta hat with this delta, I want that to be smaller than the variance with that delta. Or if I'm comparing these two deltas, the smaller variance wins. And I can do that for any vector C that I care about. Now, sigma squared is going to cancel out of that ratio. So from now on, sigma squared equals 1. We'll just measure y in units of sigma. Okay, so we don't have to worry about sigma squared. What vector C should I look at? It'll turn out that they're all kind of the same, but I want the C that measures the value, and I'll say what that is. Okay, here's the incremental value. If we give somebody the incentive, then Z is +1, and we're expecting beta 1 plus beta 2x, beta 3, beta 4x. If we don't give them, then it's a -1. Then this is the expected return. The sign here changed. We went from beta 3 to negative beta 3. So that's a gain of 2 beta 3. And we get 2 beta 3 and 2x beta 4. Okay, so that's the difference that it makes to us. For a customer at point X, this is how much extra or less y we're going to get on average. So clearly beta 3 and 4 are important. The intercept could never be important. Everybody gets through the intercept. That won't affect your decision. Okay, well, what about the variance of that thing? Okay, so chug, chug, chug. Here's the variance. And let's look at that variance formula. X squared is in the numerator. Delta is in the denominator. If I have a good X or a bad X, well, first of all, the bigger X squared is, the more variance I'm going to get because I'm extrapolating. But that factor, it's the same for every delta. Also, if I have a good delta or a bad delta, it's the same for every X. Okay, so we're lucky. This came out pretty simple. Okay, let's plot the variance. This is the coefficient of z, and this is the coefficient of z times x, and we can plot their variance as you go from no experiment to fully experiment. And what we see is the more experiment you do, the less variance you get. And this curve up here, it's exactly triple this curve. Okay, so if we do a regression discontinuity design, we get variance 12. And as we switch over to an experiment, it comes down to variance 4. So the more experiment you do, the better. And what about at some value x? So we could have a customer with a running variable here, or x, could go out to say the best possible customer a priori, and it's symmetric. We can go down to -1, and the curves would just be symmetric. And now let's look at n times the variance. This is a log scale. The top curve is what happens if you use regression discontinuity. And so you get this variance. The further x is from the decision point, the more variable it gets. Now let's dial in 10% experiment. It's better. 20, 30, 40, 50, 60, 70. Down here, we're at 100% experiment, and the variance is a lot lower. What's interesting to me is the worst variance when you did a full experiment, it's still better than the best variance if you did regression discontinuity. Okay, so there's regression discontinuity is shooting a lot of noise into your situation. It's a lot of sampling variance. We're still not going to do 100% randomized controlled trial though. Okay. Here's the expected payoff that we're going to get from the n customers. Okay, so 1 over n customers, I equals 1 to n. This is the expected y, so there's an intercept. That's not going to depend on our delta. There's x. That's actually not going to depend on delta either. If I average this, it averages to 0. There's beta 3 times the z's. That's actually going to average to 0. The only thing that really will be interesting is this last one, whether z and x interact, and that's why beta 4 gets to be red. So let's talk about the gain if I did delta, and that's the expected value of the payoff averaged over all n of them. And with a bit of calculus, it's beta 1, the intercept with a gimme, and the only other thing that comes in is beta 4. And here's delta. That's how much experiment we did. And it has a negative coefficient. What that means is the more delta, the worse off you are. I'm assuming beta is positive, that the higher ranked customers gain even more from the incentive. Okay, so if delta is large, you get more statistical information. If delta is small, you get more value from the incentive you're offering this year. So it's an exploitation kind of trade-off. And okay, so how would you trade that off? Well, one way would be to say, I want, hello?
Yeah, can I interrupt for just a second?
Yeah.
This is super cool. Could you maybe remind me how you were calculating the payoff?
Yeah.
Because there's some assumptions there in modeling that payoff.
Right.
Obviously.
So up here is yi. So I'm assuming that the user of this, they want more y. And so this is what the model says y is going to be. And so now I'm going to average it over customers 1 to n.
I see.
And so that's like suppose you're giving out some incentive and you're going to get back like $200 per customer on average, or $150 per customer. And what happens is the more you experiment, the less on average you're going to get back. Or for the scholarships, if you give the scholarship to the wrong students, maybe you'll have less people graduating than if you gave it to the top students.
Right.
That's the point of that one.
Yeah. That's
okay.
Super cool.
Okay. Well, thanks. So if I'm choosing between 0, which is regression discontinuity, and some other delta, then the ratio of the variances comes out to be this formula. So if I want to be at least this much better than regression discontinuity, I have to do at least this much experiment. And I'll show you some numbers. If I want to be 20% more efficient, I better experiment on 18% of the data. If I want to double my efficiency, I have to experiment on 43%, which isn't a whole lot. It's not like I have to experiment on 99%. So there's a little bit of experimentation can bring you big gains. Okay, so somebody asked earlier about like a sliding scale. So what if we sort the customers and we have their probability of getting the incentive right up on, this is a Gaussian, or it could actually be in steps. And in the paper with Hal Varian, there's no advantage to doing this and maybe a disadvantage. So that was a bit of a surprise because starting this, I thought this was actually going to be the thing to do, to dial it in on a smooth curve. And it turned out it doesn't do you any good. Here's another example. The airline's not going to give frequent flyer a first class upgrade to half the people. Maybe they'll give it to a few at the top and then a few more at random, and almost everybody doesn't get it. So we have an analysis of this. Suppose 15% will get the incentive. And then in this framework, the variance is like 223 over n. But now suppose you give it to the top 10% and then half of the next 10%. Okay, so the top 10%, they still get it, but you've got 5% more to dish out. Spread that evenly. Now your variance drops and the ratio is like 1.6. So it's 60% more efficient to shoot in that smidgen of randomness. Okay, well, so that was for this model that I told you was wrong. What's more popular, and this is where I switched to joint work with Dan Kluger, is to use kernel smoothing methods. So the expected return, it's not really linear in X. If Z would be positive, it's a smooth curve mu plus of X. And if Z is negative, it's a smooth curve mu minus of X. And so what do people do? They do kernel estimates. So we'll take this squared error for observations, and we'll do a kernel weight right around the threshold, the target point. That's what they do for regression discontinuity. And what's this kernel bandwidth? It could be as simple as if the argument is below 1, it's a 1, otherwise it's a 0. So then we would just be looking at every data point within distance h of the threshold. So that's by now the more standard way to do regression discontinuity. And here's an example on that data from Israel. So here are classrooms that just barely didn't get split. Here are class sizes that went with 41, so it got split. I'm showing you before it got split, 42, and these are in the 40s. And here are the local linear regressions that the kernel method says to use after picking the kernel. And you can get a 95% confidence interval for the advantage of a small classroom, and it goes from minus 1.4 to plus 7. Okay, nobody said that confidence intervals can't have 0 inside them. This one does. Well, it turns out that in regression discontinuity, that target, it's always outside the data interval. Your smooth curve for the pluses, you're extrapolating from x bigger than t down to the threshold. And on the left-hand side, from x smaller than t up to the threshold. So it's all about extrapolation. And then you use the difference. And there's some theory that says if you're going to extrapolate, I mean, if you must, use a triangle-shaped kernel, not a boxcar kernel. And that goes back to Cheng Fen and Marum. And so this is what people do for regression discontinuity. They use a triangle kernel regression. If you did a triangle kernel, we end up with a slightly smaller kernel, and we get a confidence interval from minus 2.4 to plus 9. This is for 4th grade average verbal score. Now, if you do this kernel smooth, a kernel smooth has bias and variance. And policy questions come down to confidence intervals. And they're easier to get if the variance dominates and you eliminate the bias. And so people tell you to use a smaller h than optimal. And so we're going to do that. And now we're just going to study the variance because we got rid of the bias. So we have a local tiebreaker. In the local tiebreaker, you rank your customers 1 to n. You pick some distribution for who gets the incentive. You do the assignment, you get the y values. Then you pick your kernel h and do your smoothing. And everything I'm talking about today is at step 2. We don't know what's going to be Y. We don't know what's going to be H. We're only up here. We haven't got the data yet. It might be 6 years before we know who came back from who graduated, or it might be 1 year before we know who bought more of our product. Okay, so we're kind of working a little bit in the blind. At the time we have to make the decision, these are not available. Later, when we get the Ys, you might use some, XGBoost or a neural net or something. We can't design for that. We're going to design for a linear model. Okay, so with the Boxcar kernel, there's a critical variable. We're going to randomize for the x's close to 0. And then the important thing is, how much did we randomize divided by the bandwidth? This is what fraction of the data that we weight, that we actually keep, was experimental. And the efficiency comes out to be this polynomial, and it's exactly the same as in the Halvarian paper. And so you can get an efficiency of 4 if delta is 1 or more. So it's still better to experiment. Let's look at the tiebreaker model. Let's look at the Boxcar kernel. Oh wait, no, it's still the Boxcar kernel. Yeah. So this is just a graph. Here's the curve, polynomial in delta squared, and here's the graph. So if you don't have any experiment, we'll say it's efficiency 1, and the efficiency goes up as high as 4 if you fully experimented. And it's a pretty smooth monotone curve. What about the triangle? Well, if we did the triangle, it kind of looks like the same curve, but if you stare at it, it only goes up to 3.6. It doesn't go up to 4. And it's monotone. Look at that. It's strictly increasing. So again, the more you experiment, the better off your variances will be. Wait, is it really monotone? Okay, here, little delta is the local amount of experimentation. So it's how much experiment over the bandwidth. Here is the formula. There's a degree 12 numerator and a degree 7 denominator. And Dan Kluger could heroically show this is actually strictly monotone. Okay, so this was epic. I'm so happy that he was able to do that. I mean, I can tell it's monotone, but it's so much better to be sure, and he nailed it. Like if you take the derivative of this, the numerator has degree 18 by the time you take the derivative. Is that a question?
I do have a question,
Yeah.
And it may be an impossible one, but
Okay.
is it reasonable to say that the intuition behind why more experimentation gives you lower variance is simply you have more opportunity to learn? It's sort of like if you're using the cutoff, you're not really learning at all. You're restricting the information.
Well, I have a different intuition. So my intuition is when you do a regression, you have more precision in the middle of your data than you do when you're extrapolating.
I see.
And then if you do a regression discontinuity, you're moving the cutoff point. It's more like the middle of the data. It's not perfectly the middle, but it's less extrapolation. So that's my way to explain it to myself.
Cool. Thank you.
All right.
That sort of goes to a question that we have in the Q&A.
Sure.
Around, and I think I know the answer to this, but I'll defer to Art about like why not, like, let's say you run an experiment.
Yeah.
Right, and then you just look at an interval within the experiment versus, like, effectively you're throwing out some data.
Yeah.
Like, well, what is the benefit of this? I think I have a sense, but.
Oh, well, it's a bias variance trade-off. Yeah. So on one of the first slides, I showed a plain linear regression where it's linear way to the left of the cutoff and linear way to the right of the cutoff. But if the data wouldn't be linear out there, then you could really mess things up. And Andrew Gelman on his blog has examples of people spectacularly messing up where they fit a cubic and the data just wiggle like crazy and they get completely non-believable regression discontinuity estimates.
Oh, no, so this person wasn't saying, or David wasn't saying that it was a discontinuity. They were saying that they have a full experiment. Okay. Right, so it's kind of like in the regression or in the tiebreaker design, you're only randomizing in a subset versus, let's say you're randomizing to everybody and then we're just looking at an interval. I think like you're throwing out some data, but like.
Well, Okay, so if I did a full experiment,
Yeah.
you know, I might fit a model to everything, or I might fit a local model. And the local model might actually be a lot like fitting a flexible model to everything. So I think throwing out data is a sort of a simplified bias variance trade-off thing. And enriching the model with more terms might accomplish much the same.
Yeah.
Yeah.
And then there's a second question from Damien around, right? So in regression discontinuity, we're told that the triangle kernel is better than the boxcar.
Yeah.
Less bias, less variance, but that smoothing the window isn't useful in tiebreaker design. Is there an intuitive way of understanding why a triangular kernel, instead of smoothing, is not also superior to a boxcar style tiebreaker region?
Wait, a triangle. Let's see. So my way of thinking about this is that the incumbent method is a regression discontinuity. And I'm telling people they should do a tiebreaker. What they were going to do is regression discontinuity with a triangle. And I'm going to say you do better with a tiebreaker and a triangle. And what could happen is you could do even more better with a tiebreaker and some other kernel that I don't know about.
Yeah.
So I'm just saying, like, if that was what you were about to do, here's how you can do better.
Yeah.
And also, once the data come in, of course, you're going to use XGBoost, or you're going to use, you know, neural networks. So you're going to do something that you didn't think about when you were designing, or you're going to at least peek at all those things. So you're going to do more. This is just to say, in a simple setting, we can tell it's going to be more informative.
Great, thank you.
Okay. Okay, so we had that unreasonable assumption that the data were equispaced, or actually, well, you could equispace them if you wanted, but let's look at the actual spacing. So in the school size data, if we look at the actual spacing, and then we pick a regression size that's either 1, 2, 3, up to say 10 students wide, we can trace out the efficiency curve. And for the triangle, it actually goes up to 4 empirically. The theoretical one only went to 3.6. But you know, that was for equispaced data. For unequispaced data, it's close to the same curve, but it's not perfect. And it's a little bit random because the z's are random. And what we did to randomize our z's, we would pair them off and toss a coin. One of them would be +1, one would be -1. So the randomizing in the z makes almost no difference. And we see, and the unequal spacing makes almost no difference compared to our theory. Okay, so that's, and then what bandwidth did we pick? Well, this is the bandwidth that people have used already for that data. We didn't want to, you know, we just said, let's take the bandwidth that everybody uses. And you notice this curve is so smooth that we don't really have to show these box plots anymore. And so that curve I showed you there, it's the Imbens-Kalyananaman bandwidth. It's this green one here. If you use a bigger bandwidth, it's more efficient. A smaller bandwidth, it's less efficient. But essentially, the efficiency curves are pretty similar. So you can expect that you should do better with a tiebreaker. You can't know how much better you're going to do, but you should expect to do better. Okay, so that was a very unrealistic setting. Here's a more realistic setting. We've got a running variable x, but you know, we have 100 variables that could be important and like 1,000 more that aren't important, but we've got a lot of variables. And we're going to use a black box predictor, f of x. And then a tiebreaker, we're going to randomize if the running variable is close to a threshold. I think we're still going to wind up, if we, you know, fit a deep learning model or an XGBoost or like random forest or whatever, I think we're going to do better if we did the tiebreaker, but I can't prove it. Intuitively, it feels like it should be better. Second, more realistic setting. Now the running variable, it's not even x1. It is our black box. So we have some old data. We do a black box prediction of what's going to happen. That's going to be our running variable. Again, we do a tiebreaker. And then a year or 2 years later, when all the data come in, we refit our black box. And I think it's going to come out better than if we hadn't randomized. I don't have any math to show you for that. Just intuition, I would expect that it shouldn't get worse. And so this is probably a bit closer to what people's real problem would look like. Okay, well, I have a lot of people to thank. First of all, it was really fun to work with Hal Varian and Dan Kluger on these projects. I think Hal and I thought we invented tiebreakers, but a little bit of a literature search, no, they're around, people did them, so we had to work a bit harder and study them. I want to thank Google because they allowed this work to come out and get published. I want to thank Brian and Zach, I misspelled, for coordinating this. There's an Algo Hour committee that I need to thank. I want to thank Stitch Fix for hosting. The National Science Foundation funded the part that wasn't Google. And so I want to thank everybody for listening through this most of an hour or two.
Awesome. Thank you so much.
Thank you.
So now's a great time for questions. Were there any questions that didn't get answered already? You can either post them in the Q&A or in the chat. Dr. Owen, can you see the Q&A now?
No, there's the Q&A button. I hit the Q&A button and Dimitri has a question.
Great.
There are also some assumptions about inability to sort around the cutoff. Are these the same in the regression, the RDT? I'm not quite sure what's that. What's the inability to sort? Like,
let me promote Dimitri to a panelist, and then I'll let him ask.
Okay. Oh, wait, study harder to get aid. Oh,
does that make more sense? Just the ability to sort around the cutoff, kind of if the experimented units kind of know about the treatment rule.
Yes, so there's a literature on people manipulating the running variable. And I saw a famous story where there was a high stakes test where you had to have 30 points in order to pass, otherwise you failed. When you look at the data, there's no 29s, there's no 28s, there's no 27s. And anything with humans involved, there's going to be something. So for instance, in the Israeli school thing, there were some principals apparently that could somehow get in a few extra kids into a cohort in order to split the class. So there's always manipulation, and there are people trying to detect and correct it. I see a question by Joshua: why optimize for variance reduction rather than expected rewards? Well, if you optimize for expected rewards, you're probably going to do regression discontinuity. And if you optimize for variance reduction, you're going to do randomized controlled trial. And so it's this trade-off. And so the point we're trying to make is start with the thing that's optimal for variance for rewards, and then dial it back a little bit to get more precision. And again, it's trade-off, so it's just really hard to get a unique best thing when there's trade-offs. If you knew how much reward was worth how much information, then you could make a linear combination of the value of your information right now and the value of your reward in the future and try to optimize the trade-off. I think that's just practically, that's probably too hard. I feel like it's hard enough to get people to tell you a prior, and it's pretty hard to get a loss function or a value of future information. So we think instead in terms of like, if I just wanted 20% more efficiency, how much more experiment would I have to do?
Yes, do you have thoughts here? Because I know that, like, I think you pointed to Gelman's critique of like some RDD designs. Yeah. And even like, I think you just mentioned a second ago about like, well, maybe some teachers can like get their students just over the cutoff. Yeah. how, like, that would imply to me that the tiebreaker design is actually way better, right? In the sense of like, you're not only are you losing in the like standard RDD setting, you're losing like it's higher variance, but also there's bias from some of these.
Yeah.
From some of these like design where the assumptions might not hold, and like how much have you thought about that?
Not a lot. I have a former student, Evan Rosenman, who's worked on detecting and fixing manipulations. I'm thinking that if United Airlines is handing out bonuses, or Stitch Fix is handing out something to their clients, they have complete control, and maybe the client can't gerrymander the way across it. So in a place where you control the assignment, you can introduce a bit of randomness. I have a question. I see a question from Eddie about why we're assuming that RDD is better at optimizing. This is because we're assuming that beta 4 is positive. And so what that means is we're going to get the most incremental value out of what are already the best customers. And that's not necessarily true. But under that assumption, then you put all of your incentives on the top group and you don't put any anywhere else. But it could be wrong.
Awesome. Thank you so much, Dr. Owen. I really appreciate you coming. And for those of you who are joining us from outside Stitch Fix, just a commercial for next week. We have Melanie Weber from Princeton, and she's going to be talking about geometric methods for machine learning and optimization. So hyperbolic spaces for representation learning, roughly. Hope to see you next week. And thanks again, Dr. Owen. This was super, super fun.
Oh, well, thank you. It was my pleasure to come and talk to you. What? And if there's I could take another question, but I also have another meeting coming up. So.
Yeah, do you recommend people email you if they have follow-ups, or?
Yeah, email's good. So cool. I'm easy to find. It's like Owen at Stanford. That's those are both easy to spell, so I think we're good.
Awesome. Awesome.
All right.
Well, thanks again.
All right. Well, thank you. This was really fun.